Okay, so let's go over reciprocals of quadratics. Now, normally a reciprocal of a quadratic function would be something like f at x, right, is equal to x squared. That's a really basic one. And a reciprocal function is 1 over f at x, which essentially means this value here is just 1 over a quadratic. This looks very different. In fact, this looks very much like a rational function. What we're going to do is we're going to split our numerator here into a more basic fractional addition question. So when I say that, what I mean is we're going to take f at x is equal to, and we're going to take the first pairing, okay, kind of put them together, and then the second pairing and kind of put them together. Because this can be rewritten as 3x squared over x squared, and then we have our addition sign, plus 1 over x squared. And just as a proof for this, think of the idea like, well, I don't know, 3 plus 4 over 5, okay? We know the answer to this is 7 over 5. We can simplify. But this can also be rewritten as 3 over 5 plus 4 over 5, and it still ends up as 7 over 5, right? So this check technically works. We can break this question down. We can kind of reverse. Instead of simplify, we can kind of expand that question. So we've expanded here, and what that helps us do is essentially eliminate the quadratic or the rational part of this function here. So now we're left with 3 plus 1 over x squared. So that now gives us a translation, okay? I'm just going to rearrange this so it looks like 1 over x squared plus 3. This plus 3 is outside of a function. So if you remember your rules for a function, where you get a at f, and then you have k, x, and I think you guys use the letter d and c, is that right?
We use different letters.
Yeah, you use different letters. Yeah. Oh, essentially the idea is the c is outside of the function, which is this case here. This is outside of the function. So what we're doing is we're taking the reciprocal of a basic quadratic and we're vertically shifting it 3 units up. So we know we're going 3 units up. Now, to get an idea of our basic quadratic, what we're going to do is we're going to just go through a couple of proofs here. One of the proofs of this quadratic, so 1 over x squared, we need to find if there's any vertical and horizontal asymptotes to it, so when we go to sketch this idea. Okay? So this is without that translation. So vertical asymptotes, essentially the denominator cannot be 0. We know we can't equal 0. So what we're going to do is x squared, we're going to set it equal to 0 and find out what values we can't have. Well, in this case, it's very simple. We square root both sides, so we find the square root of 0, which is 0. So x can't be 0 in this case. That's our idea here. So what that means is we have a vertical asymptote, so a line that will never touch at, and this is technically where, x is equal to 0. So it's a line vertically going up and down through the value of 0, or essentially the y-axis on this one. The second one here to find a horizontal asymptote, and we probably have a horizontal asymptote because this looks what's usually known as a rational function, where we have we essentially have a denominator variable with a, if we were to get rid of that as a denominator, essentially it is a negative exponent. Okay, so that's the idea here with a rational function here. So we need to find a horizontal asymptote, and one of the proofs to this is to, and we'll take the same function, is to divide. Essentially, we're going to try to take x to its limit. So we're going to be substituting, and in this case, it's x squared, right? But we're going to take x to its limit. So we'll take x squared, and we want it to essentially be the value of infinity. So what I'm going to do, just to get an idea of what this will be, is I'm going to divide both the top and the bottom of this fraction by x squared. So that's going to be 1 over x squared and x squared over x squared. Okay? So then we're going to plug in our infinite value here. So this becomes 1 over an infinite number, so it's an extremely large number, and an infinite number squared, which is essentially an infinite number, divided by an infinite number. So let's talk about the top of this. Because infinity is such a large number, we're essentially getting a huge value. Think of it like a billion course, much larger on the bottom, which when we go to divide that on a calculator, essentially we're getting something that's extremely close to 0. So it's like going 1 divided by 99999. So try to take the calculator as large as possible, and this will probably round us to the value of 0, right? So in other words, this value on top we can essentially say is 0. On the bottom of this, sorry, let's make that black. We have infinity, or an infinite value, divided by an infinite value. Well, that's the same idea as like 5 divided by 5. It's a value of 1. Okay? So now we have 0 divided by 1, which in our case is 0. So what that's telling us is we have a horizontal asymptote at 0. And now you don't always have to do this proof. Usually the best way to do it is you just look at the coefficient in front of the variable on the bottom. So the coefficient is 1, and technically you could say the coefficient in front of x squared here is 0. We take 0 divided by 1. We just take those two coefficients and divide them, and that'll tell us the horizontal asymptote. Well, 0 divided by 1 is what we got from this proof. So essentially it's 0. So what we've now got, if we're going to graph something like this, and we'll just do a rough sketch, what we found out, okay, and we'll actually sketch it out after, is that we have, and here's our y and our x, right? We said we had a vertical asymptote at x is equal to 0, and we had a horizontal asymptote when y was equal to 0. Okay, so we'll do them in two different colors here. So we have a vertical asymptote right here, so along the x-axis and the y-axis, and a horizontal asymptote here. Okay, now what that means is we have some function that's either going to go up like this, maybe come down, maybe it comes over here, maybe it's over here. So we do want to test out where this idea is. And one of the things we can do to do that is find a negative x value, like -1, and plug it into our equation to find out where the original is. So at this point, I'm specifically talking about just 1 over x squared. Okay, so let's say we want to plug in at -1. Where is this value? So it becomes 1 over -1 squared. So it becomes 1 over 1. So essentially we're positive, and that's what's important to us. We're positive, so we're above this horizontal asymptote. So in other words, we're above here. So knowing that this can't go below this line or across this line, we probably have something that straddles the lines like this and then goes up. Okay, we would use calculus to find any other bumps and turns in there. And we're going to do the same thing with +1. It's a simple value. Same idea, and we're going to end up with 1 over 1 squared, which is 1 again, which is important that we're positive, above the horizontal asymptote. So again, we have a function that probably looks something like this. We're not below it. Now what we said from this original question, we've gone quite a far away from there now, is technically we had 1 over x squared plus 3. So we're taking this above function that we have, and we just kind of discovered how to draw it, and we're vertically shifting it 3 units up. So the vertical asymptote won't change. That still exists. But the horizontal asymptote is going to move up 3 units. So we now have a vertical asymptote. I'll do it in green again. I'll call this the number 3 here. And we could use a real graph, which I should in a second. But essentially, let's say that's at the value of 3. Okay, so our new graph is doing the same idea. It's above that horizontal asymptote, and it's probably doing the same thing. It's just higher up on our sketch. Okay, so this has been vertically shifted 3 units up. There's quite a bit of stuff there. To give a good graph of this, here's the original I'm talking about. And you'll notice we have a vertical asymptote coming down the y-axis, a horizontal one coming on the right, and here's some values we can kind of run across this line. And they're at -1 and 1. That's one of the values we said, and it kind of takes off. It's almost exponentially. And same idea, coming closer and closer, but never touching. Now, the original question they gave us, actually, let's go to how we split it. When we split it up, we said we're going to take this original one and move it up 3 units. And that's essentially what happens here. If you notice, it's getting close to 3, right? We're at 3.01, close and close and very close, but we're never touching 3. So the horizontal asymptote has been moved 3. And this is the exact same as this. All we did was break that version down to get what we now show up as in green. Okay? Does that make sense?
Right.
Yeah.